All right, so this is where we left off on Tuesday, and these are some equations that I'm going to give you on the exam. Okay, so these are equations that you will have. You do not need to memorize them, okay? But let's just talk about this a little bit. Okay. So here, this is where we left off, right, Eric? Okay, page 7. Right, so this is chapter 18, okay, Ecell, okay, which is the anode and the cathode, okay? So this is looking at a battery, okay, voltages. All right, thank you, Lee. All right, voltages, all right, so we must remember voltages, okay? We must remember that a positive voltage means that electrochemical cell is favoring the products. Okay? We don't buy negative voltage. We buy 9-volt batteries, 12-volt batteries. We don't buy negative 9-volt batteries, negative 12-volt batteries. So if you see a positive voltage, this favors the products. Okay, on the flip side, if you see a negative voltage in the reaction, okay, in your electrochemical cell, this is a reaction that favors the reactants. Okay, so this K is the equilibrium constant. So this is chapter 18. Chapter, 16 was the equilibrium constant. This is products over reactants. Okay, we do not put solids, we do not put liquids in this. Okay, and we raise it to the coefficient. Okay, you remember this? And here, if you remember, if your K is large, even though this is unitless, let's just say I give you $1 million. Okay, are you moving forward or backward in your life? Okay, for most people, giving someone $1 million would make them move forward in whatever aspect of their life. Okay, for a reaction, which is products over reactants, no solids, no liquids in this thing, if the K is greater than 1, this is something that favors the products. If K is less than 1, very small number, okay, it means you'll have more reactants than products in this ratio. That means your reaction or your electrochemical cell, your redox reaction, will favor reactants. Okay. All right, so that's equilibrium. This is electrochemistry. Okay, and then finally thermodynamics. So here, delta G, standard state. Okay, notice all of these are standard state. Standard state, and K is usually at equilibrium. Okay, otherwise if you're not at equilibrium, we call that Q. And we use Q to compare to K. So delta G here is called the Gibbs free energy. And we're looking to see if the reaction is thermodynamically, from the perspective of thermodynamics, is it favorable or not? So here, if your delta G is negative, it is exergonic. And if your delta G is positive, it is endergonic. So this triangle relates these three equations. Okay. Like I said, I'll give this to you on the exam. Okay, so whatever you need. You want to relate thermo to Ecell. You want to relate K to delta G. You want to relate K to Ecell. These equations do it. All these equations represent standard state. And all these equations represent some form of equilibrium where the reaction is settled. What do I mean by settled? It means like either reactants are going to be more or more predisposed to products. Okay? There's no shifting. The reaction has settled. Okay? If it's not in equilibrium, it will shift according to Q, which is the reaction quotient. All right? So this is plug and play. Okay? Whatever equation you need, you'll do this. Right? So what is the situation that favors products? Positive voltage, because again, we buy positive voltage batteries. A K that's larger than 1, and a delta G that is exergonic. Okay? If you take a thermodynamics class, or maybe biological chemistry class, or a biochem class, they tell you that if the reaction is exergonic, it favors the products. Alright, so, and if delta G is positive, what does that mean? Endergonic reaction favors the reactants. We call that an endergonic reaction. Okay? Alright, so I'll give you these equations. Let's plug and play with them. I'll give you this. You have to choose which of these three equations. Notice that we are merging or we are unifying electrochemistry, equilibrium, and then thermodynamics. We're sort of bridging them together. All right, so let's do some problems together here. Calculate the equilibrium constant for the following reaction at 25 degrees C. 25 degrees C. Okay? So when we see this problem, or when you see this, encounter this problem on the exam, what you need to do is you need to break this down. Okay? You need to break this down. So iron plus 2 goes to iron. Okay, we'll do this in blue ink. Just go like this, iron. Right, so a question for you guys is how many electrons and where does it go? How many electrons and where? Product side or reactant side? 2 electrons on the 2 electrons on the not products. Okay, so so let me explain why it's on the reactant side. So what's 2 electrons? Minus 2. What's plus 2? 0. Minus 2 plus 2 is 0. What's on the product side? 0. Yes? Okay, it's 0. Is this, now here's a question for you guys to see if you've been catching up or studying. Is this a reduction reaction or an oxidation reaction? Okay, we are gaining 2 electrons. So is this reduction or oxidation? Reduction. Yes, reduction. Okay, now another question for you guys. Reduction occurs where? The anode or the cathode? Red cat eats an ox. So according to red cat eats an ox, this is the cathode. Okay? So what is the voltage? We will get our table out. Make sure you bring this to the exam. Okay. And where do we see iron plus 2 electrons goes to iron solid? Where do we find it? Okay, I'm finding it right here. minus 0.44 volts. Do we flip it? Okay, we will not flip it, right? Because this is a reduction, and this is also a reduction. So minus 0.44 volts is what it's going to be at. So that's one. Okay. Next, we're going to take Ag solid plus Ag plus. Okay, I'm just ignoring the 2's because literally the 2's cancel out. Is this okay, or you want me to keep the 2's? Okay, basically I'm taking this and breaking it down and building it back up. Taking this, breaking it down, and build it back up. When I build it back up, I'll regenerate this original equation. So I'm going to cancel out the 2's in this half reaction. Okay? Okay, just cancel them out. All right, how many? Ag plus. Okay, Ag solid goes to Ag plus. Everyone see that? All right, how many electrons and where should they go? One on the product side. Is this the cathode or the anode? Well, if this is the cathode in blue, what will this have to be in black ink? It has to be the anode. Okay, lose electrons. All right, let's have everyone go back to our sheet here. Okay, what do we have for this? Ag solid and Ag plus. Yeah. Do you guys see it here? Right, what should we do with this half reaction? What do we need to do? I mean, is this going to be positive 0.80 volts? Yes or no? What should it be? Okay, first of all of these are the cathodes. This is the anode, so what should this be? Not positive 8.0 volts, but it should be negative 0.80 volts. Okay. All right, I'm going to multiply the bottom by 2, so this is a 2 electron transfer reaction. Okay, this is a 2 electron transfer reaction. The bottom one here is an oxidation. You lose an electron. Okay, multiplying the bottom by 2, I just want to tell you guys this is a 2 electron transfer reaction. Alright, so let's rewrite this again. We have 2E minus plus Fe plus 2 aqueous. Fe solid. Two Ag solid goes to 2 Ag plus 2E minus. Alright, so this still stays at minus 0.044 volts. I multiply the bottom by 2. What will this be? The same, minus 0.80 volts. Remember, all of these numbers do not change. What changes? The only thing that changes is the sign. The only thing that changes is the sign. Alright, so this is a 2 electron transfer reaction. This electron cancels out with that electron. We're going to call this Ecell, which looks to me to be about 1.14 volts. 1.24 volts? 1.24. Negative. Okay, negative 1.24 volts. The final net reaction is going to be 2 Ag solid, basically the same as this. So we deconstructed it and constructed it back together, getting Ecell. 2 Ag solid plus Fe plus 2 goes to Fe solid plus 2 Ag plus aqueous. Okay, this is what we need. And now we have, I think, everything to calculate the equilibrium constant, okay, which is called K. All right, so you guys tell me, which equation shall we use? Okay, we'll use this equation. There's some constants in this equation that I will tell you, and I will give those constants to you on the exam. But we're going to use this equation to get K. Okay, we'll use this equation to get K. And let me write that down. Our first constant, and I'll give this to you. Okay, I'll give this to you on the exam. The first one is F, which stands for the Faraday constant. This is 96,500 joules over volts. Okay. Joules over volts. Okay, so that's a constant. I'll give that to you. So you do not memorize any constants. Okay, R here is 8.314 joules over mole Kelvin. All right, so again, this is just plug and play. Okay, what is N? N is the number of electrons that are being transferred. In this particular problem, this is a 2-electron transfer reaction. Okay, so N is the number of electrons being transferred. Okay, so let's do this. Ecell here is minus 1.24 volts. R is 8.314 joules over mole Kelvin. Now, you know, K is unitless, so really I'm not going to bother with units, because let's remember it was a question on the exam. K has no units. Okay, pH, POH, K, they have no units. R is 8.314 joules over mole Kelvin. I mean, we don't have to bother about units. F is, what is F? 96,500 joules over volts. Okay, what is N in this particular problem? N is 2. Okay, T is the temperature, and the temperature given to us in this problem is 25 degrees C. Okay, and that's 298 Kelvin. Okay, and all of this times natural log of K. Do you guys know how to solve for K now? All right, I am going to do this and take minus 1.24 divided by that. Okay, so let's do this on our calculator. I think I may need to borrow our calculator because my one just died. Do you have one, Eric? Thank you. Okay, I appreciate that. Oh, this one? All right, I'll work this out. He has one of the harder calculators to manipulate. All right, let's do this together. Thank you for the calculator. Mine crashed and burned. All right, 8.314 times 298 divided by 2 times 96,500 is 0.01283 blah blah blah. Okay, so 0.01283 natural log of K. 1.24. Natural log of k equals minus 1.24. I'm going to avoid the units here. All right, so minus 1.24 divided by 0.01284. Okay, equals natural log of k. Okay, so take minus 1.24 divided by that number. So I'm getting about minus 96.59. Okay, so e to the power of this should give me k. Okay. Let's see on Eric's calculator how we can do it. Getting 1.12 times 10 to the minus 42. This looks to be the answer. All right. So just make sure on the exam you know how to do this plug and play on this equation. All right, a couple of things here. Actually, one thing. 10 to the minus 42, is that a small number? Yes. Okay. Minus 1.24 volts. What do we call that? Okay, we call that a dead battery. Okay, don't work. Okay, so this by the K tells us this is not favored. The voltage negative, the voltage being negative tells us that this is not favored. So you see how everything corroborates with one another? Okay. Yeah. All right, let's do another one here. I will have your calculator with me, Eric. Wait, actually, you know what? You can use your calculator and check mine because I have a, yeah. Oh, good. Check my answer also. Thank you, sir. All right, calculate delta G for the following reaction at 25 degrees C. Okay, so like before, I'm going to take this, break it apart, and build it back up together again. So if I'm going to break it apart and put it back together again, I'll just omit these coefficients because they'll come back when I build this back up again. So we'll break this down to cathode and anode, break this down into reduction and oxidation. The first thing we see here is Al plus 3 goes to Al solid. All right, how many electrons and where does it go? All right, so this is going to be 3 electrons on where? The product side or the reactant side? Okay, reactant side. This is cathode because you're gaining 3 electrons. Right, let's look at our sheet and see where Al is. Al plus 3 and Al solid. So bring this to the exam, and I printed out a whole bunch of copies the other day. Here we go. Can you do this with me? Okay, minus 1.66 volts. Right, and now in blue ink we'll do magnesium solid plus magnesium plus 2. All right, how many electrons and where should this go to balance out? Right. Is it okay if I tell you it's 2 electrons on the product side? Is this correct? Yes, this is correct. Is this the cathode or the anode? This is losing 2 electrons, so we're going to call this the anode. And now, where is this? Magnesium solid and Mg plus 2. Where's that? I see it right here. Do you guys see it with me? Magnesium solid, Mg plus 2. But what do we need to do with this number? What do we need to do to the minus 2.37? Okay, we're going to flip it because this is a cathode reduction. In this problem, Mg is anode oxidation. So we're going to flip this to positive 2.37 volts. Okay, we're going to get Ecell now, which is anode and cathode coming together. Okay, before I do that, okay, no free electrons. Okay, no free electrons. Get them out of there. How do we get them out of there? Okay, we're going to take the top one by 2, and we're going to take the bottom one by 3. So how many electrons are being transferred here? Okay, this is 6. This is a 6 electron transfer reaction. This is a 6 electron transfer reaction. Alright, so this becomes 6E minus plus 2Al plus 3 goes to 2Al solid. Three Mg solid goes to 3Mg plus 2 plus 6E minus. Okay, so this Ecell becomes, what's 2.37 minus 1.66? 0.71 volts positive. Okay, so this is our Ecell. Positive 0.71 volts. Okay. Joining these guys together, the 6 and 6 cancel. We're left with this. Okay, we broke it down and built it back up, but in the end, in that process, we got Ecell. So we have 3 Mg solid plus 2Al plus 3 aqueous. Okay, this is going to go to 2Al solid plus 3 Mg plus 2 aqueous. Okay, with an Ecell of positive 0.71 volts. Alright, so now that we got Ecell, we can calculate delta G. And it's just a matter of choosing which equation we want to choose here, choosing which equation that we will use. And I think I'm going to use this equation, okay, because this has what I need to get delta G standard state. Okay, so you make sure you choose the right equation. I have F, which is a constant. We just calculated Ecell. N, what is N here? N is 6, very good. Right, so we're going to use delta G naught is minus NFE cell. Okay, minus 6, 96,500. Here you want to use the correct thing here, joules over volts, and Ecell is 0.71 volts. So we get joules here, and then what's minus 6 times 96,500 times 0.71? Okay, this is minus 411,000 joules. This is the answer. Now you can divide it by 1,000 and get minus 411 kilojoules. It doesn't matter. Okay. here's something I want to tell you guys, one point, okay? The point is this. You see the minus 411 kilojoules? Okay, the minus sign tells us this is an exergonic reaction. And an exergonic reaction liberates free energy. This is energy that has the capacity to do work. So the delta G is negative. Okay, this favors the products. Okay, what does this tell you about the positive voltage, 0.71 volts? It too favors the products. So the electrochemical cell is positive, so we have a battery. The free energy is negative, which means it favors the products. Okay, all of these corroborate one another. Okay, the electrochemistry corroborates the thermodynamics. Okay, by the way, just as a review, let's see. Okay, what if on the exam you're asked to write this in galvanic cell notation? Galvanic cell notation. What is that? The galvanic cell notation is this. Anode couple, Mg solid. Okay, draw one line, Mg plus 2. Okay, anode couple, salt bridge. How do we describe a salt bridge? Two straight lines down. Cathode couple. Cathode couple. What's our cathode couple? Al plus 3 aqueous. Okay, draw a straight line down. Al solid. Okay, so now we're going to the last part of our chapter, the last part of our course. Okay, we got what, page 9, 10, and 11. And let's see if we can finish this off once and for all. Okay. All right, another equation that I will give you on the exam, this is called the Nerst equation. Okay, so I will give you this equation on the test, and it's plug and play. But what does the Nerst equation really tell us? Okay, it tells us the voltage for non-standard state. So I want you to associate the Nerst equation with non-standard state. Okay, non-standard state. All right, so what is non-standard state? Okay, 300 degrees, 50 degrees, okay, 0.6 molar, okay, 0.25 atmospheres, okay, anything that's not standard state. Standard state, I'm so sorry. Okay, standard state, I gotta turn off that phone. I don't even know how to use the phone on my own phone, so I don't even know how to use that. So, standard state is a very specific set of conditions. 1 atmosphere, 25 degrees C, okay, 1 atm pressure. Non-standard state is something that's not one of those, okay? All right, so we're talking about non-standard state. We're going to use this equation. Now, there's two forms of this, okay? There's the log form or the natural log form. Okay, so I will give you one or the other. I think more than likely I'll give you this form that you can plug and play. Make sure you know how to use this. Okay? So two things I want to tell you about this Nerst equation. Nerst equation. Number one, we have Q here. Okay, we use Q and compare it to K. Okay, there's three situations that could happen. Number one, Q can be greater than K. Q can be equal to K, and then Q can be less than K. Okay? So what's the situation where Q is greater than K? The alligator jaws point to the reactant side. And when the alligator jaws point to the reactant side, okay, basically this favors the reactants, which implies a negative voltage because the alligator jaws or gator claws, whatever, it points to the reactants. Favor reactants, and this is a negative voltage. This is a dead battery in all essence. Okay, what if Q is less than K? Where do the alligator jaws point? Okay, the alligator jaws point to the product side of the equation. Okay, this is a positive voltage, and this is essentially a battery. And then finally, if Q is equal to K, it favors neither. Okay, and that's 0 volts. Okay, so that is not negative, not positive. It means no battery. Okay, no battery. Okay, you can also, yeah, no battery, it's fine. All right, so this is the equation we will use. What is N here? Okay, number of electrons transferred. Okay, N is the number of electrons transferred. All right, so we'll use this Nerst equation here. Here's my second point I want to tell you. You notice to get Ecell, you need Ecell at standard state. Just like remember this equation from our previous chapter. To get delta G, you need delta G at standard state. This is one of the equations that we used. Okay, it's the same thing here. Okay? To get delta G at non-standard state, some other conditions, we need the delta G standard state. Okay, to get Ecell non-standard state, we need the Ecell standard state as part of our equation. All right, let's practice using this equation on these next set of problems here. All right, will the following reaction occur spontaneously? Okay, we're looking for a positive voltage at 25 degrees C, given that the iron concentration is 0.60 molar and the cadmium concentration is 0.010 molar. Okay, so are we at standard state? Okay, no. If we were at standard state, this would be at 1 molar, and then the cadmium also would be at 1 molar. Both would be at 1 molar. So we're not at standard state. All right. So we're going to do what we've been doing all along. We're going to break this down. Okay, so the first thing is cadmium goes to cadmium plus 2. We'll do this in black ink. Excuse me. Okay, how many electrons and where will it go? How many? 2 on which side? Okay, this will balance out the charge. 2 on the product side. And is this oxidation or reduction? We lost 2 electrons. That is oxidation, and oxidation occurs in the anode. Okay, anode. Okay, let's look at cadmium here. Okay, what do we need to do with this number? Flip it. You guys see that we need to flip it? Yes, we need to flip it. So this is positive 0.40 volts. Is everyone okay with me so far?
Yeah.
Right? Everyone good?
Nice.
Did I lose my water bottle? Did it drop somewhere? Oh, there it is. Okay. I'm too lazy to go get it up, pick it up. All right, so now we have, in blue, we'll do Fe plus 2 goes to Fe solid. Let's go ahead and do that quickly. Fe plus 2 aqueous goes to Fe solid. How many electrons and where should it go? Okay. Do you guys see 2 electrons on the reactant side? We'll balance this out. Is this the anode or the cathode? This is the cathode. And what is the voltage with this? Negative 0.44 volts. Everyone see this? Negative. All right, so now we got that. This is a 2 electron transfer reaction. Okay, this is a 2 electron transfer reaction. All right, so this makes this Ecell, which is negative 0.04 volts, right? 0.44, yeah. This is non-spontaneous under standard state conditions, but we're not under standard state. Okay, we're under these conditions. But under standard state, this would be negative and not a battery. All right, our net reaction is going to be Fe plus, our net reaction is going to be this. Okay, we just broke it down to anode and cathode. All right, so we got this, but this is not the answer because that's under standard state conditions. We want it under these conditions, okay? 0.60 and 0.010, okay? And Q, first of all, let's use this equation here. E is equal to E standard state minus 0.0257 volts. Okay, N, what is N? Okay, this is a 2 electron transfer reaction. Okay, natural log of Q. What is Q? Okay, it's going to be concentration of CD plus 2 divided by the concentration of Fe plus 2. Okay, Q. And why did we not include iron solid or cadmium solid? Because these are solids. Okay, we'll plug in the concentrations here. Ecell, okay, I'll plug that in. This is negative 0.04 volts minus 0.0257 volts divided by 2. Natural log, what's the cadmium ion concentration? 0.010 divided by the iron. What's the iron concentration? 0.60. Okay, and this will be our answer. All right, now let's do this on our calculator and see if your answer is the same as mine. All right, 0.01 divided by 0.6. Is that, and we will take the natural log of it. Okay, natural log of this is this crazy number. Natural log of that times negative 0.0257. Okay, I want everyone to pay close attention. Times, not a positive, but what? Times a negative. Okay, times a negative 0.0257. Okay, divided by what number? Divided by 2. Plus, everyone look here, plus a negative 0.04. Plus a positive? No, plus a negative 0.04. Okay, can we do this on our calculator? Okay. And then I'm getting positive 0.013 volts. Okay, make sure you put the units of volts in, voltage. And this is our answer. Notice under standard state it's not spontaneous, but if you play around with the concentrations of the anode cadmium and the cathode iron, if you play around with the concentrations, you can get it to be a little bit, tiny bit positive voltage. All right, are we okay in using the galvanic cell notation? Okay, what is that for this one? Okay, anode couple. Draw one line down, cathode couple, salt bridge. What is the salt bridge? 2 lines down, anode couple, and then finally the cathode couple. Plus 2, iron plus 2, draw one straight line down, and then iron solid. Okay, so that is the galvanic cell notation. You'll be able to go from here to here on any exam. Okay. Able to go from here to here. Anode couple, salt bridge, cathode couple. All right. Our last 2 problems, and then you guys are done with all new content. Okay. All right. So we go through, get this over with. All right. Do I have your blessing to move on to page 10? I think everyone is. All right, EMF stands for electromotive force of a galvanic cell consisting of a cadmium plus 2 cadmium half cell and a hydrogen ion, hydrogen gas half cell if the cadmium is 0.2, hydrogen ion is 0.16. Pressure of the H2 gas is 0.8 if the reaction is to happen spontaneously. If the reaction is to happen spontaneously. All right, so let's go ahead and do this problem. Are we in standard state? Okay, no. Okay, standard state means 1 molar. So we have the cadmium plus 2 cadmium half cell. Okay, let's go ahead and write this down. I see it right here. Okay. Cadmium plus 2 to cadmium. I'm going to write this. Okay, this is minus 0.40 volts. Okay, the hydrogen ion, hydrogen gas. Okay, platinum is just the electrode because hydrogen is in water, and gas, it's a gas. Hydrogen is a gas. So don't worry about the platinum. Okay. In fact, this is how I think this is how your pH meter works. But anyways, here this half cell is H plus and H2 gas. Where's H plus and H2 gas? I do not know if you know this, but this is, I didn't teach you this, but this is set as baseline 0. Everything is relative to this. All right, so we're going to write this down. We're going to flip 1, okay, because remember, 1 has to be the anode, the other has to be the cathode. Okay, so let's write this down. Okay, don't worry about the platinum. Okay, it's not part of this. 2H plus 2E minus. Goes to H2 gas. And that's 0.00 volts. All right, so let's highlight something here spontaneously. Okay, spontaneously. Okay, that means a positive voltage. So we need to flip one. Okay, which one do you want to flip? To make it the anode, to make it oxidation, which one do we want to flip? Top or bottom? Okay, we will flip the top half reaction and make it the anode. Okay, so I'm flipping that. CD solid goes to CD plus 2 aqueous plus 2E minus. Okay, this is positive 0.40 volts. H plus 2E minus. That's 0.00 volts. Okay, so like we said before, this is the anode and this is the cathode. Two E. 2H plus aqueous plus cadmium solid goes to cadmium plus 2 aqueous plus H2 gas. Okay, this is Ecell now, cathode and anode, and this Ecell now has become Ecell. It's become 0.40 volts. All right. So that is at standard state, but we are not at standard state. Okay, we're at this state where the cadmium is 0.2, the hydrogen is 0.16, and the gas is 0.8. Okay, hydrogen gas. So let's calculate Q first, and then get the voltage here. Okay, EMF means voltage. All right, so Q is going to be the pressure of H2, products over reactants, times the concentration of CD plus 2 divided by the concentration of H plus, and we need to square it. Okay, we have to square this. Q, just like K, has no units, so Q here is going to be 0.80. Okay, the cadmium ion concentration is 0.20. And then the H plus concentration is 0.16. And then we got to square it. Okay, we got to square it. All right, so 0.8 times 0.2 is 0.16, I believe. Yeah, 0.16. So 0.16 divided by 0.16 squared. 6.25 is Q. Okay. All right, so we got our Q and we got our Ecell. Now what equation we will use? We will use the Nerst equation to get our final voltage under these conditions. All right, so once again we plug and play with the Nerst equation. I'm going to move it up here. Ecell is equal to standard state cell minus 0.0257 divided by n natural log of Q. Okay. By the way, what is n here? What's n? Okay, this is a 2-electron transfer reaction. Electron transfer reaction. So we calculated Ecell here to be positive 0.40 volts minus 0.0257 divided by n, which is 2. Natural log of Q, okay, it's products over reactants. I got 6.25, so natural log 6.25. All right, can we do this on our calculator? Okay, natural log of 6.25 is that number. Okay, times a negative 0.0257. Okay, are we going to do times 0.0257? No. We're going to do times a negative 0.0257. Okay, and make it negative. Okay, negative. Plus 0.4. Plus 0.4. I'm getting about 0.35 volts. And this is, I believe, the answer. So notice at standard state, we have a battery between cadmium and hydrogen. And also if you tweak the concentrations, you can get it a little bit lower. Okay, a little bit lower voltage. All right. Can we do the galvanic cell notation? Okay. Anode couple, which is CD. Draw one line. I'm sorry. Can we do the galvanic? Take two. Can we do the galvanic cell notation? Okay, anode couple. Yeah, I got it right the first time. CD solid, one line, CD plus 2. What's a salt bridge? Salt bridge is 2 lines cathode couple. Where's my cathode couple? It's going to be H plus. You can do 2H plus or just write H plus. Draw a straight line down, H2 gas. So that is the galvanic cell notation. This and this should be, interchangeable. All right, so this is how we do this type of problem. This is the Nerst equation. Nerst equation. All right, this is our last problem, and we have how many more minutes? A good 10 minutes or so. Okay, we've got a good 10 minutes. All right, so consider the following diagram. Magnesium solid goes to MgSO4. What do these two lines symbolize? Okay, the two lines symbolize a salt bridge. Nickel sulfate at 0.6 molar, nickel solid. All right, so two things about this that if you see this on an exam. Number one is that this magnesium sulfate is actually Mg plus 2 and SO4 minus 2. Okay. And then along the same vein, this nickel sulfate as ions, 0.6 molar ions would be nickel ion, and SO4 minus 2 ions. And now, how do we do this again? Anode couple, salt bridge. Okay. Highlight the salt bridge with 2 lines. And then cathode couple. All right, so Mg solid goes to Mg plus 2. How many electrons and where should it go? 2 electrons on the product side. And what's the voltage associated with this? It is Is it negative 2.37 or positive 2.37? Magnesium solid goes to Mg plus 2, losing 2 electrons. Okay, so that's an oxidation. This is the reduction. So we're going to flip this and make it positive 2.37 volts. This is the anode. All right, our salt bridge is here. And then we will do the other one. Nickel plus 2 goes to nickel solid. Okay, we'll do that in blue here. How many electrons and where? Okay, 2 electrons on the reactant side. This is the cathode. I'm seeing this right here. And this is minus 0.25 volts. Minus. So that is the cathode where reduction happens. This is a how many electron transfer reaction? Okay, this is a 2 electron transfer reaction. All right, so now we have our Ecell. 2.37 minus 0.25 is 2.12 volts. Positive 2.12 volts. All right, let's just rewrite this reaction. Nickel plus 2 aqueous plus magnesium solid. That goes to Mg plus 2 aqueous and nickel solid. Okay, so this is not the answer. This is at standard state. Okay, are we at standard state? Okay, the answer is no, because we have our Mg plus 2 at 0.4 and we have our nickel plus 2 at 0.6. Okay, so let's go ahead and use what is called the Nerst equation. Okay, the Nerst equation is this. I'll give this to you on the exam. Oops, sorry. E is equal to Ecell minus 0.0257 divided by N, natural log of Q. Okay. All right, what is Q here? It's the concentration of Mg plus 2 divided by the concentration of nickel plus 2. Okay, Mg plus 2, as we find here in our notation, is 0.40 molar. And nickel plus 2 here is 0.60. All right, so what is that? 2/3? 0.4 divided by 0.6. Okay, 0.6667. Let's plug everything in here. So Ecell, we just calculated it as 2.12 volts minus 0.0257. This is a 2 electron transfer reaction times natural log of Q, products over reactants, and this is 0.667. All right, can we do this on a calculator? All right, make sure we are comfortable doing this on a calculator. All right, we're going to take the natural log of this. Okay, times a negative 0.0257 times 0.0257, but make sure you put a negative in there, times a negative. And then we will divide this by 2. And then add 2.12. And I'm getting about 2.125, you could call it 2.13 volts. Okay, and this is the answer. All right, really quickly, the last one here. How does the cell voltage change when the magnesium is decreased by a factor of 4? So when the magnesium is decreased by a factor of 4, the new magnesium concentration will be not 0.4. Okay, when it decreases by a factor of 4, the new magnesium concentration will be 0.1. 0.1. So let's quickly solve this problem, substituting 0.1 in here, and then we will wrap things up. Okay, so the new Mg plus concentration, when we decrease it by a factor of 4, is 0.10 molar. Okay, so our Q now is 0.10 molar divided by 0.6, and that's, what is that, 0.166666, something like that. Yeah, 0.1167. Okay, let's plug it back into this equation here. Alright, so we'll plug it in here. East cell is still 2.12 volts minus 0.0257 divided by 2. It's still a 2-electron transfer reaction, but now it's a natural log of 0.167. We decreased magnesium by a factor of 4, making it from 0.4 to 0.1 in part B. And what is this going to be? Okay, times a minus 0.0257. Okay, divided by 2 plus 2.12. Okay, plus 2.12. About 2.14 volts. Okay, 2.14 volts is the answer. So honestly, with me, if you are going to make a battery with magnesium and nickel, you can probably use less magnesium, right? Why waste magnesium? Okay. Why waste magnesium plus 2? Okay. If you decrease it, quadruple the decrease, you still get the same voltage. Actually, you get more voltage. Actually, if you decrease the magnesium, you slightly get more voltage. So this is a wrap of chapter 18. I got 3 more minutes with you guys, so we are finished with the course, so we can give ourselves a round of applause. And we will review on Tuesday, and then Thursday we'll take our test. Okay, I do not know when the final is, but I think it's posted on the university website. And for next week, I'd like to have your lab report and your notebook. So as long as everything meets the mark on your lab notebook, I'll give you 100 points. Been keeping up with the signatures and such, and so we'll make that due next Monday, Tuesday. Okay, I think next week is the last week of school before final exams. And anything else? So turn in your chapter 18 homework. And anything I am missing? Oh, I do have your exams. They are in my office. I'll go to my office, pick them up. And if you're here, I'll hand them out. If not, I'll give them to you later. All right. So have a good weekend. Have a good Friday. Tomorrow is a holiday. Now, anybody want their exams? Nobody wants their exams. All right. I'll bring them to you on Tuesday, unless you want them. Okay. Just come to my office.
Have a good Easter.
Thank you, Carson.